Hey everybody, welcome back to chapter 12. We're going to continue our discussion about z-tests and single sample t-tests. Let's get us some more practice. Here's a bit of review. Which of the following is false? Well, let's start from the bottom up. Sigma is the standard deviation of a population. Mu is a mean of a population. Mu and x bar are both means, which are calculated the same way, even though one's for a population and one's for a sample. Now, sigma and S, standard deviation of a population and standard deviation of a sample, those are not calculated in the same way. So that is A is false. You'll remember way back to when we were talking about descriptive statistics, the population standard deviation just has population size in the denominator, whereas for a sample, the standard deviation has n minus 1, and that is basically a correction factor because sample standard deviations tend to underestimate population standard deviations. And remember, the whole point of the class is to estimate something about a population from a sample. So we need to make this little correction to make it so that we're not accidentally underestimating the population standard deviation from the sample standard deviation. Some more review here. When do you use a z-test or a one-sample t-test? So that is going to be D, when we want to compare the mean of a sample to the mean of a population. It's not when you want to find the relationship between two variables, that's correlation. It's not when you want to compare the means of two different samples, that is independent samples t-test. We're going to talk about that pretty soon. It's not when you want to know if one variable predicts the other variable, because that is regression. So it is D, when you want to compare the mean of a sample to the mean of a population. The difference being you have to use a t-test if you don't know the population standard deviation, and you use a z-test if you do know the population standard deviation. Here's another one. What information do you need to run a z-test? So you're going to need a few of these things. You are definitely going to need to know the population standard deviation. You don't need to know the number of people in the population. You do need the population mean. You do need the number of people in the sample. You do need the sample mean. You do not need the sample standard deviation. Okay, similar question, but what information do you need to run a one-sample t-test? Well, here, the whole point of a one-sample t-test is you don't know what the population standard deviation is, so that's why you can't run a z-test. You have to run a t-test if you don't know the population standard deviation. So you don't know that. You don't need to know the number of people in the population. You do need to know the population mean, the number of people in the sample, meaning the sample size. You do need to know the sample mean, and you do need to know the sample standard deviation, because we're estimating population standard deviation now with sample standard deviation. So you can see that the formula for a one-sample t-test is almost identical to the formula for the z-test, except the denominator is now, instead of standard error, it's called estimated standard error, because you're using sample standard deviation to estimate the population standard deviation. So that's really the only difference here. Also, I just want to note, anytime you conduct a t-test or try to find a t-score for anything, it's also called the t-obtained, the obtained t-value. And that's to distinguish it from a critical t, the t-crit, that you look up in the t-table, and then you're going to compare your t-obtained to your t-crit, your critical value of t, to decide whether your obtained t-score is significant or not. All right, let's start doing some examples. So I think that CU Boulder students are more stressed than the general population. The mean stress for the population is 5 with a standard deviation of 2. So already right there, you're given the standard deviation of the population, so you should know which statistic you're going to try to calculate. I sample 18 CU Boulder students. Their average stress level is a 6. Let's say this is out of a scale of 1 to 10. So I want you to figure out what statistic are you trying to calculate, what test are you trying to run, and go ahead and calculate it for me. So from the previous slide, you know you have the population standard deviation. So automatically that means you'll be running a z-test in this case if you're trying to figure out the difference between a sample mean and a population mean. So if you use this formula here and you plug in the values from the previous slide, you end up with a z-score or an observed z-score of 2.12. So the previous hypothesis was that we think CU Boulder students are more stressed than the population, which is a directional hypothesis. Let's pretend like we actually made a non-directional hypothesis that CU Boulder students are just have a different amount of stress than the population, but we don't know in which way. So if we make a non-directional hypothesis like that, we're going to use a two-tailed test. Okay, if we did that, and we found a z obtained of 2.12, would that be significant? And what would you do with the null hypothesis? Well, in order to figure that out, you'd want to compare that obtained z-score against a critical z-score, and you look up critical z-scores from the z-table or the normal distribution table. If you have a two-tailed test, you need to look up a p-value of 0.025 because we split alpha, which is 0.05, in half because we have half of it in each of the tails, right? So if you look up on the z-table a p-value of 0.025, you can see that the corresponding z-score is 1.96. Now that'll be a negative 1.96 and a positive 1.96 because we're talking about both sides of the z distribution here. Now the question is, when you compare the observed z-score of 2.12 to the critical z-score, both negative 1.96 and positive 1.96, what happens? Well, the z-score of 2.12 is more extreme than 1.96. It's more extreme and it's further to the right. So because the critical value 1.96 sets up a critical region where anything to the right of that is shaded in fact, we do see that our observed z-score falls within that critical region, and therefore we get to reject the null hypothesis and conclude that we do have a significant result. Significant what? How? Well, it means that the sample mean of stress for CU Boulder students is significantly different than the population mean for stress. That's what it means. All right, another example here. I think my students drink more coffee than the population. The average cups of coffee for the population is 3 cups per day. I measured 20 of my students. They drank an average of 5 cups of coffee per day with a sample standard deviation of 2 cups of coffee. So, what test are you going to run to see if the sample has a different amount of average coffee drinking than the population? And what is the obtained score that you calculate? So since you don't know the population standard deviation, you're going to run a one sample t-test, right? You've got all these pieces of information. If you plug them in from the previous slide, you should get an obtained t-score of 4.47. Now you already knew this slide was coming, so if we had a directional hypothesis that in fact, my students drank more coffee on average than the population. Therefore, we would use a one-tailed test for the one sample t-test. Would an observed t-score of 4.47 be significant? And what would you do with the null hypothesis? So we got to find the critical t-value and compare our observed t-score against that. We look up on the table. First of all, in the columns, we know we have a one-tailed test with a significance level of 0.05. In the rows, we know we have a sample size of 20 students. But for a one sample t-test, the degrees of freedom equals n minus 1. That is important. So we actually look for 20 minus 1. Degrees of freedom should be 19. Follow it across, and you see that the critical t-score in this case is 1.729. So we put that on the graph over here, and you can see that an observed t-score of 4.47 is way, way, way to the right. It is way more extreme than the critical t of 1.729. So our observed t-score does indeed fall in the critical region, and therefore we can reject the null hypothesis and conclude that there is significance here. Significance in meaning what? It's a significant test, but what does that mean? Well, what we were trying to find with our hypothesis was whether or not students in my sample drank on average more cups of coffee than the general population. And because we are seeing such an extreme observed t-score and it falls in the critical region, we reject the null hypothesis that there is no difference between the means average cups of coffee consumed, and conclude that in fact, yes, students in my class drink much more coffee than the general population on average. All right, thanks everybody. Now you know when you need to use a z-test or a one sample t-test. Have a good day. See you in the next video.